Okay, so we'll be talking about further about diagonalization in this lecture. So, more on diagonalization. So, remember last time we did a sufficient condition for an operator to be diagonalized, and it was based upon uh, the fact that if the characteristic polynomial has n distinct roots, then your operator is diagonalizable. Now we are going to uh, come to a very beautiful theorem of linear algebra, and basically uh, it states that, so the theorem states that a complex normal matrix is always diagonalizable. So the converse is also true, uh, that a matrix is diagonalizable if a matrix is diagonalizable if it is a normal matrix. So this part is rather easy. So let's focus on the first part of this. So this is part 1, this is part 2. So what do we mean by a normal matrix? So well, the normal matrix is normal when it commutes with its Hermitian conjugate, or that is m dagger is equals to m dagger m. This is a normal matrix. So notice how this theorem is so beautiful. It connects, uh, is that this condition is so easy to check by a simple computation. M, the Hermitian conjugate transpose, again you can just take it, multiply, and you can check it. So this can be checked by simple computation. By contrast, whether M is diagonalizable seems much harder to check. This condition is very easy to check, but whether or not M is diagonalizable, let's say by a unitary matrix. Uh, so by diagonalizable, we mean M is U D U dagger. This is some unitary matrix, and this is a diagonal matrix. So checking this condition seems to be a much more convenient way rather than trying to figure out whether or not trying to find the use where this format holds. But the theorem says that these two conditions are equivalent. And the reason why we are interested in diagonalization is that diagonal matrices are much easier to deal with, as we have already seen in the previous lecture. So how do we go about this proof? Uh, so essentially there are two ideas to the proof. So two ideas to the proof. Well, the first idea is to observe what do we gain by m dagger is equals to m dagger m. So this, what does it mean? It means that the length of the jth row, length of the jth row is equal to the length of the jth column. So we can write m as, we'll just check it for the first row. So let's write this as matrix as this. So this is the first row, this is the remainder of the matrix. So this is m. Uh, we can check that what will m dagger mean. So I'll just, m dagger would be, again, this r would come up as r conjugate over here, and then that would be some m star. And when we take m dagger, this row multiplies with now what has become the column. So essentially I'll get something like r dagger. You can check this. This would be the first element and some over here. This is m dagger. Similarly, if I write m in terms of its column vectors, I'll write it as c m prime and double prime. Let's say this is the same matrix, but now it's written as its first column and then the remainder of this matrix. And if I take m dagger m now, we can check that this, after multiplication, this is going to be the first element, so on and so forth. So when m dagger and m dagger m are equal, that means that r dagger and c dagger c are equal. So this implies r dagger is equals to c dagger c. This is nothing but, if you look at it, this is the length of the row and this is the length of the column. So that's something very interesting about normal matrices which we have observed. This is merely our observation. Now let's try to figure out how are you going to use this. So we already know that since m is a matrix over the field of complex numbers, we have the characteristic polynomial, this guy, and by fundamental theorem of linear algebra we know that this has got at least one solution lambda, at least one solution lambda. So there is an eigenvalue essentially, and in the basis of its eigenvector, it has got one eigenvector. If it has one eigenvalue, m can be written as lambda something 0 and something. You can check that this is going to be the eigenvector of, so we've written this first column as the eigenvector. But now we know that what does the normality condition holds in any basis. So what does the normality condition imply? Well, the normality condition implies that the length of the column is equals to the length of the row of the first column. This holds for any of the column, is equal to the length of the first row so that means that the remaining entries of the first row better be 0. Then only you will have the length of the first column and the length of the row equals. So I can show that m is of the form lambda 0 0 and something over here. So due to the normality condition, I mean, you can check if this is the matrix with the normality condition and I put m dagger is equals to m dagger m, then these entries have to be 0 as well for the matrix. And this is the kind of a matrix I have. So now what do we have? We have reduced M to be a matrix where is of the form of this with some other structure, and we can apply this whole thing recursively, which is to say we'll have a characteristic polynomial of this guy, again reduce this guy to some particular form. Let's say this is the M1, and argue on the basis of normality condition, length of jth row equals to length of jth column, and again argue that this is of the form of some lambda 1 where these entries have to be 0. Keep recursively applying till we get this in a diagonal form. So that essentially is the trick. Recursively, my suggestion is that you guys go after the class and try this. Recursively applying this idea to the bottom right block in the matrix, we can diagonalize them. We can diagonalize M. So how beautifully we have shown the connection between normal matrices and the ability to diagonalize it. So how are you going to prove the other way around, that if the operator is normal, then it is diagonalizable? Or so we've just shown that. How would you prove that the converse part of this sort of a thing, where if a matrix is diagonalizable, then it is normal. So diagonalizable implies it's normal. So even in fact that part is also rather easy. There's not a big deal about it. Think about it. How are you going to do that? See, one suggestion is to decompose any matrix into so let's say if I have a matrix M, or just a second, I can always decompose a matrix into two parts. So I have a matrix M, and I can write it as A plus iota B, where A and B are Hermitian matrices. Okay, So now what do we do? So what does the fact that these matrices are diagonalizable, what does it yield? So in order to diagonalize this matrix, uh, what does diagonalizing M means? That means to diagonalize M, we need to be able to simultaneously be able to diagonalize A and B. Is it correct? So, and what does that yield to us? If I can diagonalize A and B simultaneously, then so to diagonalize M, we need to simultaneously be able to diagonalize A and B. So we know that if matrices are, we are able to diagonalize the matrices simultaneously, then well, then they commute. That's, I hope you've learned that in quantum mechanics. We can go over it and try to actually show it as well. But that essentially is the idea that if we are able to, so just let us write it down. Uh, so this implies A and B are simultaneously diagonalizable, A and B commute. So A and B, I can write A as M plus M dagger divided by 2. B is M minus M dagger divided by 2 iota. Remember, I started with M equals to A plus iota B, this guy. So once I have this, uh, then what do I have? I have A, B commute since they are simultaneously diagonalizable. Remember, now I am trying to prove that if the matrix is diagonalizable, trying to get the condition of matrix. So what does it give me? That essentially gives me plugging in the values of A and B into this equation. That will give me the condition M and M dagger commute. You can check it. That's rather easy to do. Plug in A as M plus M dagger by 2 and B as M minus M dagger by 2 iota and try to show this sort of a thing. So mind you, this is the way you can decompose any arbitrary matrix as a sum of two Hermitian matrices with a complex number. This is much like breaking down a complex number into real and imaginary parts, something like that, very akin to it. You can do it for matrices also. That yields me this condition. So normalcy implies diagonalizability and diagonalizability implies normalcy. So that was a good part. Uh, we just did that. Okay, so what do we have? So now we have covered in a very systematic way this notion of diagonalizability. So we can also study a few properties of Hermitian matrices since we already dealt with it. Most of you know about these things. So Hermitian operators, the definition is that operators or matrices, well, A has to be equals to A dagger. That's by definition the definition of a Hermitian operator. And they are very important in quantum mechanics. It can be shown that they have got real eigenvalues, something which you can easily prove. Uh, So what do we show over here? So we can show this connection between so first of all, we observe that how do we diagonalize such a matrix, or what will be. So we've already shown that since Hermitian matrices are a very special case of normal matrices, certainly a dagger is equals to 0 when a is equals to a dagger. So these are diagonalizable matrices. So what is a change of basis or diagonalizability? What is the type of matrices which would in general diagonalize or inflect a change of basis of Hermitian matrices? So this is my change of basis, which gives me the Hermitian matrix in another basis, and I demand that P inverse dagger uh, is equals to A prime itself, because ultimately A prime is equals to A prime dagger. So what do we have? And I also have this A is equals to A dagger. So let me just expand it. So I get, when I take the Hermitian transpose, I get A P inverse dagger, P dagger, because I am taking the dagger of this over here times the dagger of this over here, and that is nothing but that gives me P inverse dagger, A dagger, P dagger. Now A dagger was nothing but A, so that gives me P inverse dagger, A, P dagger. So that is the change of basis I have for the Hermitian matrix, and essentially what do I get from this sort of a change of basis? I demand that just a second, what was I supposed to prove? Yeah, so this I want the dagger of this has to be equals to this itself, because any matrix transpose conjugate is equals to this matrix. So this matrix taken times dagger should be equals to this particular matrix. So I have P inverse equals to P inverse dagger A P dagger. And one of the ways to satisfy this is when P inverse is equals to P dagger, or P dagger P equals to I. But the bottom line is that this is when P is a unitary matrix. So the change of basis for Hermitian operators, the ones that diagonalize it also, because even expressing a matrix in terms of its eigenvectors is a change of basis. So it's the unitary matrices that inflict the change of basis for Hermitian matrices. So this is something interesting about Hermitian matrices. The other thing is that what about simultaneous diagonalizability, which we have already seen. Simultaneous diagonalizability, we used it earlier, but let's just see it formally. So I have two matrices A1 and A2, and what does simultaneous diagonalizability mean? It means UA1 U inverse is some matrix D1, UA2 U inverse is the same unitary matrix that diagonalizes both of them. This gives me D2. So, well, since these are diagonal matrices, I have D1 D2 minus D2 D1 is equals to 0, and I can again write, since this is there, I can write U inverse D1U is equals to matrix H1, U inverse D2 U equals to, let's say, H2. So this condition boils down to nothing but U inverse D1 D2 U minus U inverse D2 D1 U is equals to 0. I can plug in U inverse here, doesn't matter, U inverse here, U and U inverse here. So the bottom line is that I get H1 H2 minus H2 H1 is equals to 0. So what does that give me? Well, if the matrices are, well, I have replaced H by A1 and A2, H1 and H2, doesn't matter. But what does it means is that if matrices are simultaneously diagonalizable, well, then they commute. Okay, so that is something again to keep in mind. So we can also show the other way around, that if the matrices commute, well, then they are simultaneously diagonalizable. So let's consider the case. We'll sort of show it in, maybe we can show it in a couple of ways. I don't know how many of you are familiar with the bracket algebra. So let's prove it first the simple way, and then we can go to Dirac's algebra and try to show it that particular way. But the essential idea is the following. Let's say I have this condition and I have U(a1) U inverse is equals to D, some diagonal matrix, and I apply the same matrix to E2. I don't know, that gives me some matrix M, and my condition that these two anyways commute yields to dm minus md is equals to 0. Where, mind you, M is not a diagonal matrix. I don't know what sort of matrix is it. So that means dm matrix is equals to md, and I can see this is a diagonal matrix with d11, d22, so on. This is some matrix with all entries m11, m12, so on, m22. This is equals to m11, m12, m22, m31, so on and so forth, and d11, d22, d33, 0, 0, 0, 0, 0, 0, so on and so forth. Okay, so what does this equality means? This equality can mean very simply, you just compare one of the elements. You compare this particular element of the parent matrix, like after the product. This means this would give me some m12 d22 through matrix multiplication, and over here that is going to give me, so essentially what I'm getting it is Mij is equals to Mij djj. That is my condition. So I'm just comparing the elements. What are going to be the elements of these matrices? So over here it's going to be d11 m12, something here, something here. This is going to be my element. I'm just considering a 3 by 3 matrix over here. So I have to compare these two elements, which is precisely what I'm written here, dii mij mij times djj. Now if the eigenvalues of one of the matrices which was diagonalized are distinct, So I have dii not equals to djj. Well, then the only way this can be true is mij is equals to 0. So if mij is equals to 0, that means all the off diagonal elements of these matrices are also 0. So this implies that mij is equals to 0 for all I not equals to j. Hence, that's also a diagonal matrix. So the same unitary transformation was diagonalizing this M as well. You can try it. This is a way. I have not used the bracket algebra, just argued on the basis that I start with the commutation relation, demand that the matrix U diagonalizes one of the matrices and leaves other as some other matrix, and then the commutation relation demands this sort of a matrix structure where if I have distinct diagonal entries, that means all m's of i's of j for the off diagonal elements have to be 0. So just check this particular definition. Just go to your home and get on the drawing board and get hands dirty with it. But that sort of is the idea. So in terms of the Dirac-Bragg algebra, uh, it's also given in your quantum mechanics book of Sakurai, which we can show. I'll just write it down as the theorem. Let me just label the pages. So the theorem says, this is given in Sakurai quantum mechanics. Suppose that A and B are compatible observables and the eigenvalue of A are non-degenerate. Then the matrix elements so these are the matrix elements of B are all diagonal. So well, recall that matrix elements of A are already diagonal in the basis of its eigenvectors. If A dagger are used as the base kits as bases. So well, we've already proved exactly the same thing here. So those of you not familiar with the quantum mechanical Dirac notation, especially the non-physics guys, just keep it as one more thing. You might as well ignore it. The entire meat we've already shown. This is exactly identical, saying the same thing in this bracket notation where this notion is a column vector and this guy becomes a row vector. Which is the Hermitian transpose of this guy. It's just a way of saying. So what do we have? So we need to examine these guys. So I just write it down as AB minus BA, where A prime and A double prime are the eigenvectors of A. So this gives me This was a commutation relation. This gives me 0 because I started with A and B commuting. So this will give me A double prime minus A prime, A double prime, B A prime is equals to 0. Now I've started with the eigenvalues being distinct, so this part cannot be 0. The only way to satisfy the 0 is that these guys are 0. So for different A double prime and A prime, these elements are 0, hence B is a diagonal matrix in the basis of A primes and A double primes and so on and so forth. So this is interesting. So mind you, we did this thing for uh, when we have non-degenerate eigenvalues. The statement holds even if there is an n-fold degeneracy. So the statement holds even if there is n-fold degeneracy. So which is to say that if two matrices commute, it is always possible if two operators commute, it is always possible to find a basis in which both of them become diagonal. So we need to construct appropriate linear combinations of, so let's say there was a degeneracy. So I have these set of eigenvectors uh, which yield the same eigenvalue. So they are n-fold degeneracy, I equals to 1 to n. So the deal is that appropriate linear combinations of the degenerate subspace which has all the eigenvectors with the same eigenvalue, I can find a basis such that B is diagonal in that particular basis. So which is to say that my diagonal matrix A, when it is diagonal, it becomes lambda, lambda, something like this. And then I have distinct eigenvalues, lambda 4, lambda 5, so on and so forth. And how does my matrix B look in this particular basis? So B becomes M. Remember, I was dealing with these guys. D, the diagonal matrix, now with some eigenvalues which are same, and M, what happens to the other matrix? So M will become in some particular basis where I'm listing it like this, M might become something like M will acquire a block diagonal form where these guys A, B, C, D, E, F, G, H, I, and this is the diagonal part corresponding to M1, M2, some eigenvalues over here. So now this is a Hermitian matrix in itself, and this is already a diagonal matrix. I can always find a basis to diagonalize this guy. So I'll have some unitary operator O identity that is going to diagonalize this guy. And what's going to be the effect of this on the already diagonal matrix? Well, it's just going to permute the bases, but the matrix is going to remain diagonal over here. So that was my D. So the bottom line is that if two matrices commute, that's the punchline, whether or not the eigenvalues are degenerate, I can always find a basis in which both of them are diagonal. Now, it was much easier to prove in the case of uh, the non-degenerate case, but as I have shown, we can show it in the case of the degenerate case also. So that was essentially about normal operators, Hermitian operators, diagonalizability, degeneracy, which you heavily use in quantum mechanics as well. Uh, okay, see you next time.